Hi there, it's Tina Smilkstein for Cal Poly CPE 133, and we're gonna go through a few of the homework questions to give you a review for the midterm. So first questions, those will be just their straightforward answers. So we will skip those. Okay, and those will be one-word answers. So let's do a design. Let's do this Moore machine right here. Okay, and that is an overlapping pattern matching problem. And all of these problems, if you can build the state transition diagram, you are in good shape. It's the state transition diagram that's the challenge. So let's see if we can get the camera so it's better aligned. Okay, and so this is the pattern we're looking for. We're looking for 01101, and we're doing overlapping, so the next pattern can actually start before you're finished with the first pattern, and that's what the red and the blue circles here are. And okay, so important thing is to go through the steps. You know, step one is understanding the problem. So looking for a pattern can be overlapping. Step two is the IO diagram. And one thing to notice here, do I have it written here clearly? I am considering this a bit stream in. So what a bit stream in means is that you have a single wire coming in. So let's try this. So a bit stream. See if we can make that bigger. My computer freezes regularly, so let's do that. Okay, so what a bit stream means is that there's a single wire coming in. And we can call that the stream. Okay. And then, since this is a pattern matching circuit, you want to know when you found the pattern. So let's just call that found. Okay, is that still in the picture? Looks like it is. There's found. Okay, and then this is a sequential circuit. It's doing one job at a time. Its first job is to find the first bit. The second job, or task, I've been using the word task, is to find the second bit. Third task is to find the third bit. Fourth task is to find the fifth bit. Fourth bit, fifth bit, and eventually find the pattern. Okay, so if inside here it's doing one thing and then another thing, then another thing, then another thing, and realize that finding the first bit and then finding the second bit and then finding the third bit, those are tasks that have to be done in a sequence. That means that, don't know why that's not, that means that you also have to have a clock. So you always have a clock. Oops, it's hard to make these lines straight. Who cares? And we'll just call that CLK. Okay, so that's step two. Step one, understand the problem. Step two, draw the IO. Okay, step three, timing diagram. So want to show somebody how this works. It's going to be kind of a pain to write this whole thing out. Let's see if I can cheat a little bit here. Okay, it's way down at the bottom of the picture, so let's move this up. Okay, let's do another one or two. Oops, it's too far over. Okay, so this will be the clock. And then let's do for the stream, let's say it starts at, what are we looking for? What's the pattern again? 0110. So it's for the question, I just asked you to do, you know, a sequence that you're actually looking for. So we want a 0 on one clock edge, we want a 1 on the next clock edge, and we want to see a 0 on the next clock edge, and then a 1 on the next clock edge. And then we want to know what found looks like. So we have stream. Okay, and then we have found. Let's see what found does. And on these timing diagrams, sometimes to make it a little bit clearer, it's good to say what you're starting at. This one changes so you can tell if it's starting at 0 or 1. But sometimes if you just have a straight line, the way to help the person looking at your timing diagram know whether that straight line is a 0 or a 1 is to put the value at the beginning. So just put a 0 here just to make it a little bit clearer. Okay, and then what I want for this one, this is a more machine. So even if it finds the pattern, well, it can only find the pattern on a clock edge. So let's see. So here's the first clock edge. Should we do that in red? So here's the first clock edge. It hasn't seen the pattern yet. Here's another. Here's another. Here's another. Here's another. Here's another. Here's another. Okay. So on this clock edge, it's only seen a 0. So it's seen the first bit. Next clock edge, it sees the second bit. Okay, so right here you've seen a 0, 1. Here you've just seen a 0. On this third clock edge, now you've seen a 0, 1, 1. And how that works is on the first clock edge, you look at stream. On the clock edge, it sees a 0. Next clock edge, it sees a 1. Next clock edge, it sees a 1. Okay, on the next clock edge, now you've seen a 0, 1, 1, 0. Okay, we're almost there. And then on the next clock edge, see a 1. That means, hey, I've seen the pattern. And I believe the specification is 0. I think it said, I'm not seeing it right now, but in the definition of the problem, I believe it said that this can only stay high for 1 clock cycle. So something like that. So that would be your timing diagram. Now looking at this, if a person didn't know if it was a Mealy or more, they could look at this and say, oh, even though this went to, the stream went to that 1, that last bit, went to that last bit right here, it didn't change until the next clock edge, so hey, that's a more. And that's step 4 to decide whether it's a Mealy or more, and the more was given in the question. Okay, so now the next step is to do the state transition diagram, and it's always nice to, I'm going to have to make the letters a little smaller here. Let's do it down to 14 or something. That might be too small. But first thing you want to do is you want to have a human-friendly name. So we're looking for a pattern, so I'm just going to call that none. Don't know if that's readable. Okay, and the next thing that you put inside your state bubble is the value that's going to go inside your flip-flop when you're in that state. But since I don't know how many states left we'll end up with, I'm going to leave that blank right now. I'm going to do that last after I make the rest of the state transition diagram. Okay. Also, if it's a Moore machine, then the output only depends on what state it's in, so you can draw it right into the state bubble. And if you haven't seen any of the pattern, then you know, make this a little more space in there. Might be a little bit hard to see. I'm going to post the solutions up so you can, if you can't see the values on here, then you can go to the solutions and see them there. Okay, and then first thing it's good to do with pattern matching state transition diagrams is to do the correct pattern. So basically the pattern that you did in the timing diagram. So let's do, there'll be a few states. Okay, and this one is not going to be none, it's going to be first, we'll call that first bit, meaning that we've seen the very first bit. Okay, and the first bit is a 0. Okay, so what this means is, here's a state. Haven't seen any of the bits. This arrow right here says that if my input is 0, then I need to go to another state that says I saw the first bit of the pattern. Okay, to be friendly to the reader of this, you probably want to do a key or a legend or whatever you want to call it, and you make it clear what the inputs are. And there's really only one. There's just stream. I'm having trouble typing with one finger here. Stream, and then the outputs. There's only one, but I'm plural, and that was found. And so now you have this little key right here, and now somebody can go to your state transition diagram. See, oh, here's the output. Oh, what's that? What is that output? Let me go to the key. There's, oh, outputs. Oh, there's just one, and it's called found. And same with the inputs. You know that the values on the arc for a Moore machine are going to be the inputs. So if you go to the key right here, say, oh, let's see. I know that's an input, but what's that represent? Or what signal is that? Go to the inputs, see, oh, stream. Oh, okay. So that's what this means. Stream equals 0. All right. So we've got two bits taken care of there, and just continuing on doing the, let's say we were just in the interest of space, I'll use a number there instead of spelling it out. And the second bit, since we are looking for the pattern 0110, we get a 1, we found the second bit. Okay, I'm going off screen, aren't I? Okay, and we may have to make smaller circles here for some reason the camera isn't catching. Whoops. Okay, gotta work on my skills here for a bit. And this isn't exactly human friendly because the first bit, it would be more informative for this to be called found a 0. And then over here, found 01. And this one, found 011. Okay, so to get there, it'd be 011. See, am I still on screen? I am. Okay, you know, we're looking for the pattern 0110. So we'll name this and let's see, can I get that last state in there? Yep, looks like it will fit. And there we go, and this one's going to be found. Okay, so let's fill in the outputs now. Second bit means we haven't found the pattern yet, so the output will be 1. Same thing here, we haven't found the pattern yet, so the output's going to be 0. We haven't found the pattern yet, so the output's going to be 0. Same thing here, haven't found the pattern yet, so the output's going to be 0. And finally, over here, we've found the pattern, so our output is 1. Our circuit is going to tell us that, hey, we found the pattern. All right, okay. So, so each circle, right now we only have one arrow coming out of each circle and no arrows coming out of the found state. But you should have as many arrows as there are possibilities for the input. And let's see what that means. Right now we only have one wire coming in for the input. So that can be either 1 or 0. That's two possible values for the input. So there should be 2 arrows coming out of each state. There is an exception. If you always go to the next state, then you might have a single arrow with nothing on it. If you have an arrow with nothing on it, it means it always goes to that next state. But in this case, we have values on the arrows right here, so that means we need a second arrow. So in this none state right here, we have an arrow for 0, so we need an arrow for 1. So if we get a 1, have we found any of the pattern? And the answer is no. So if we get a 1, we still haven't found any of the pattern. We're still in none. Okay, and the first bit, we have an arrow for 1. We have to figure out what to do for 0. Let's see what we've seen so far. We've seen 0. Okay, let me write the pattern up here we're trying to find. We're trying to find 0, 1, 1, 0, 1. Okay, right here we found a 0. If we find a 1, now we're at 0, 1 right here. 0, 1, 0. Okay. If we get, so since we have an arrow for 1, we need an arrow for 0. Okay, so if we get a 0, the question is where we go. This is what we've seen so far. This would be your new bit. And you're definitely not going there, but you have to think about what your pattern is. This could be the first bit of the pattern still. So what actually happens is, since this could be the first bit, if this was 0, 1, 1, 0, 1, you'd have that pattern. This new bit, this new 0 right here, that could be the beginning of the pattern. So that can still be the first bit, so you have to go back to itself. Okay, over here you have 0, 1. You have an arrow for 1, so now let's see. You have to figure out what happens if you get a 0. So this is what you've had. To get to this state, you've seen a 0 and a 1. You have an arrow for 1, so you have to figure out where the arrow for 0 goes. If you have a 0, this is not going to be the pattern, so you can look at this. You can go back to the very first bit. You have a 0, 1, 0. That's not the pattern. So next thing to check is 1, 0 part of the pattern? No. 0 is 0 part of the pattern, and that could be the first bit again. So one trick you can do is, okay, so let's do that trick on this next bit right here. If we are there, that means we've seen a 0, a 1, and a 1. You've already seen that. Okay, and we have an arrow for 0. So the arrow that we need is an arrow for 1. So if you write 1 down there, what you can do is you can take now all 4 of these bits and see if it matches the pattern. Okay, 0, 1, 1, 1, that doesn't match the pattern. The pattern is 0, 1, 1, 0. Okay, so taking all 4 bits doesn't match the pattern. What you can do next is get rid of this first bit and see if 111 matches the pattern. Does 111 match the pattern? Nope. Okay, next thing you do is, since the last 3 bits don't match the pattern, take the last 2 bits and see if it matches the pattern. So, nope, doesn't. Okay, and then take the very last bit and say, oh, does it match the pattern? And no, it doesn't. So that says you have to, you have to start over. Sorry about that. I ran into something on my desk with the mouse. All right. Okay, so if we get over here, 0, 1, 1, 0. So that's what we've got so far. We have an arrow for a 1. Oh, I didn't put whether this is a 1 or 0. We've got a 0 coming out of here, so this arrow right here is for a 1. If you made it to this state, you've seen a 0, a 1, a 1, a 0. And you have an arrow for 1, so you need an arrow for 0. You put that on there, doing our whole trick here. You look at all 5 bits now. Does that match the pattern? Nope. Okay, and take the last 4 bits. Does that match the pattern? No. To match the pattern, this would have to be 0, and then it still wouldn't match. Okay, then take the last 3 bits. Does it match the pattern? Nope. Take the last 2 bits. Does it match the pattern? Nope. Take the last bit and see if it matches the pattern. And yes, it matches the first bit of the pattern. So this needs an arrow that goes back to here. And this is a 0. Okay, I've got everything but the last state. Last state is found, and if we are allowing overlapping, let's do red and let's do really thick line. If we're allowing overlapping, see what we've seen so far. We've seen 0, 1, 1, 0, 1 if we've got to this state. So let's try 2 things here. Let's try a 0. Now we already know that these 5 bits match here, so let's start looking at 11010. Is that part of the pattern? Nope. 1010, is that the pattern? Nope. How about 010? Nope. 10, nope. And so this 0 right here, the only possibility for that is that it's the first bit of the pattern. So if we get a 0, we've got to go back to here. Okay, and now let's try the other possibility here. The other possibility is that this is a 1. So now we go through the whole thing. We know that these 5 bits right there match the pattern, so we're going to start looking at that. Is 11011 the pattern? Nope. Is 1011 the pattern? Nope. Does 011 match the pattern? And yes, 011 is actually the first 3 bits of the pattern. So if you get a 1, you go back to here. Okay, so I didn't explain it very well, but if you take the bits that you've seen so far, add on your new bit, and first look at all the bits, and then get rid of the first bit over here, look at the last 4 bits, and then the last 3 bits, and the last 2 bits, and the last 1 bit, and if any of those, the first one that matches the early bits of your pattern, that's where your arrow needs to go. Ask me about that if it's easier to do kind of pointing and talking to a human on that one. Okay, so once you have your state transition diagram, next thing is our tables, and I will put that on the homework. Again, I believe that the most challenging part of these questions is the state transition diagram, so that's why I'm drawing them up here. Okay, so that's a Moore machine. Let's give a Mealy machine a try here. Okay, I think that's still in the window. Oh, it's a little bit off to the side, I believe. Do you have the homework? Yeah, wow, it's cutting off a lot. Instead of drawing the timing diagram right here, now we're looking for the same pattern except with a Mealy machine. So let's just do the state transition diagram for this. That's cut off a little bit. Alright, so let's use the same key and okay, we're going to have some states. I'm just going to draw some circles up here. And move them a little closer. Okay, oops, I'll be chopped off. Alright, and then let's name these. This can still be none. Okay, now the big difference between the Mealy and the Moore is that because the output can change when the input changes, you take the input, you make a pair. You make a when you draw the value for the input, put slash and then what the output is for that particular input. Again, since the output can change with the input, kind of pair the output with a particular input, right? Input slash and then the output. Okay, so let's do the same thing. If we're finding the correct pattern first, and we'll write first. And so to find the pattern, your input would be 0. And if your input 0, then your output's 0. And notice the key is the same. It's just that now this is the input right here, this is the output. Still go over to this table, the key right here, and say, oh, okay, yeah, this is input, let's see what it is. Oh, it's called stream. This is the output because it's on the right side of a slash. Go up here, and oh, it's found. Alright, so then right, 1, that's the input, and for that particular input the output is 0. Okay, third, so second bit would be 1, still haven't found it, so that's 0. Another circle in here. Whoops, didn't do a great job on drawing that one. Let's do so you need another 0 there. Okay, and one more circle. Let's call that. Oops, sorry, didn't need that one. Okay, and then we'll just draw it going off into space for now, but here's your next arrow, and if you see a 1, then you've found it. You found your pattern. Okay, so let's do the arrows that we don't have on each state. And again, there's 2 values stream could be, so there needs to be 2 arrows coming out of each circle, except in the case where you always go to the next state, then you can just have an arrow there. Okay. Alright, so right here again, same as with the Moore machine. If you get a 1, you still haven't found any of the pattern. So you stay here, and your output's going to be 0 because you haven't found the pattern. First, if you found the first bit, 1, so you need an arrow for 0. Same thing as the Moore machine. If you found a 0, that 0 could be the first bit of the sequence. So you go back to first bit. Second bit, same reasoning for a second bit. If you find a 0, 0, 0. Okay. And same thing for third bit. If you have a 0, you're still on pattern, but if you have a 1, that means that you need to start over again. And you haven't found your pattern, so your output 0. Okay, this is where things get different. If you found the fourth bit, that means that you've found 0, 1, 1, 0. If you find a 1, that means you found the pattern. This also could be the first 2 bits of the next pattern. It also could be the next 2 bit, the first 2 bits of the next pattern. So for this is different than what you did for the Moore machine. Let's see, for second that would mean you've seen 0, 1. So if you saw 1, you'd actually be going to there. Okay, that takes care of the 1 case. And then the other one is that you could be getting a 0 here. So you'd have 0, 1, 1, 0, and then you could be getting a 0. Okay, and going through the same thing. Same idea over here. You look at all the bits and you say, okay, is that the pattern? No. And you look at the last 4 bits. Is that the pattern? No. Last 3 bits. Is that the pattern? No. Last 2 bits. Not the pattern. Look at the last bit. It's a 0. So that goes back to. Not sure if this is still on the camera or being cut off. Oh my goodness, it is being cut off pretty badly. Okay. Well, do I have to do that all over again, maybe? Okay, let's just go back and do the fourth. Because everything up to the 4th bit is the same as the Moore machine. It's just when you are at this 1, 1 right here, if you look at that, that gives you, to get to this 4th state, you have to have seen 0, 1, 1, 0. If you get a 1 there, then you have this. Yes, it's your pattern. But if you notice, the last 2 bits right here could be the start of a new pattern. So you have to go back to second right here. If you get a 0, then you have this pattern. And if you look at all 5 bits, that's not the pattern. Last 4 bits, that's not the pattern. Last 3 bits, it's not the pattern. Last 2 bits, it's not the pattern. So you get to this last single bit right here, and hey, that could be the first bit of a new pattern, so that has to go back to first. Okay, and then from there, the tables will be on the homework solutions. Okay, one thing we haven't done on here is we haven't assigned state values. In other words, the value that goes into the flip-flops. As practice for one-hot encoding, let me assign states to this first Moore machine right here. I'll only do Moore. Mealy is not really any more complicated. It's just that we haven't done it in class, so it won't be on the midterm. But to do one-hot encoding, you count how many states you had. So right here, there's 1, 2, 3, 4, 5, 6 states. There's 6 states. So that means we need 6 bits. And I'm just going to name it, I'm just going to let the 1, 2, 3, 4, 5, 1. Each state, the bit is going to be moved over 1 space to the left. So first one was 5 zeros and a 1. Next one is 1, 2, 3, 4, 1, 0. So 4 zeros, 1 and a 0. 1, 2, 3, 1, 0, 0. Okay, the 1 is just traveling across the number. And then 1, 2, 1, 1, 2, 3. Is that right? Okay. And then 0, 1, 1, 2, 3, 4. And then 1, 2, 3, 4, 5. Okay, so for one hot encoding, this is not minimal bit encoding. So far we've been doing mostly minimal bit encoding. We've said, okay, how many states do we have? We have 6 states. Okay, how many bits do we need to give each state a unique name? And that would be 3 bits. And that's the minimal bit encoding. And then we'd give them names like 000, 001, 010, 011, 100, something like that. That's different than one hot encoding. That's different than the state name. It's different than this 1 and 0 name that we give to each state for one hot encoding. For one hot encoding, only 1 bit can be 1. Still have to have a unique name for every state, but only 1 bit can be 1. So let me move this out of the way. Okay, is that still on the screen? Okay, so let's do the logic for this. Okay, so first let's do let's figure out output. So the output was found. Okay, and found is, you find the states where found is 1 and you OR them. Okay, let's see what I mean by that. So I only see one state where found is 1. And if you take this number that's in the state as its present state, there's only one state where PS that would be 0, 1, 2, 3, 4, 5. There's only one state where present state 5 is 1. Okay. If there were more states where there were where the output was 1, you would take them and let's say there was a present state. Let's say there were this is just going to get confusing, but you would OR them. You'd say present state 5th bit or present state 3rd bit, something like that, to find this logic. And this is bad that I'm giving you an example here that I can't show that to you, but we did that in class. If you have any questions on what happens when there's more than one state with an output that is 1, come talk to me. Okay, so that's our logic for output. We're done. Okay. And the strength again of one hot encoding is that you don't need tables. Right, so let's find next state 0. Okay, so for next state 0, what that means is that we're going to find all the situations where if the clock ticked, this first bit would be 1. The first bit of this name would be 1. Okay, if you go up here, there's only one place where the first bit is 1, and that's in this state. So for this to be the next state, you're in some other place, the clock ticks, and you go there. Okay, so to figure out where this is the next state for, you look at all the arrows going into the state. And I see 2 arrows going into the state, so there's going to be 2 terms that are ORed here. So let's look at the first one. If you are already in this state and you get a 1, you go back to the state. So that would be PS 0, and let's see, I have to make a dot instead of using a dot. I'll make a little dot there. Okay, so that's one value it could be. So if you were in the state, in other words, if PS0, this first bit right here, is 1, and the input is 1 and the clock ticks, this is where this bit right here, next state 0, would become 1. But there's another time that when the clock ticks, you would go to the state. That is in, if you are in this state, which, let's see, that's 0, 1, 2, 3. If you were in that state, and let's see, 0, 1, 2, 3, yeah, and stream equaled 1. Okay, to get all of the logic, you need to do this for next state 1, next state 2, next state 3, next state 4, next state 5. So there'll be more equations than the minimal bit logic, but each equation will be simpler. Okay. If you go to next state 1, that means the second bit right here is 1. So for this one, you see how many arrows are coming into it. It's any arrow going into a state means it is a next state for what's at the other, whatever's at the other end of the arrow. So here's 1 arrow coming in, 2 arrows coming in, 3 arrows coming in, 4 arrows coming in. This will have 4 terms right here. Next state 2, if you go over here, count how many arrows coming in. Oh, there's just 1 arrow coming in, so this is just going to have 1 term. 3 only has 1 arrow coming in, so that's just going to be 1 term. 4 only has 1 arrow coming in. 5 only has 1 arrow coming in. So all of these are going to be very simple. They'll be just a single term. Okay, that's not the greatest explanation I've ever done of any of this, but I hope it will help a little bit for those of you that are trying to get the hang of this. And I will be on Skype Sunday night. Okay, thanks.